Hello everyone, this is Bandgar working as assistant professor at Department of Physics at HM College, NASA. Today we are going to discuss M.Sc second year paper 3 experimental technique in physics semester 3. Today we have to discuss the concept of quantum physics and their various concepts. Starting with impingement rate of molecules on a surface. Number of particles which hits a surface per second and unit area at constant pressure. That is the known as the impingement rate of molecule on the surface. The impingement rate is defined as the number of particles incident upon a unit surface area per unit time and is given as Z. That is the impingement rate in Z direction is equal to NA into P upon 2 pi mRT. So this total square root is equal to P upon square root upon 2 pi MAT. So NA upon R is replaced by constant K value. So here Z is the impingement rate, Z direct impingement rate in Z direction centimeter square per second. M is the molar mass, gram per P is the pressure in T is the temperature in K, N is the gas molecule, is the sum of 2.635 into 10 raised to K is the Boltzmann constant, K is equal to R upon is equal to 1.380 in 10 raised to minus joule per R is equal to ms. So that is the impingement rate of body on the surface estimate of number of particles incident upon a unit surface. Now, next concept is the mean free path, denoted by lambda. The mean free path is defined as the average distance traveled by a gas molecules between collisions with the walls of the container or the other particle in the system. The mean free path it depends on the gas molecule diameter and the temperature and pressure. So you will get the mathematical expression lambda is equal to KT upon square root 2 pi d square. So here lambda is a mean free path. It is the meter. D is the molecular diameter of the gas molecule. It is the meter. P is the pressure. That is the Pascal. K is the Boltzmann constant, that is the 1.38 into 10 raised to minus 23 meters square into kg per second square K. T is the temperature into a K. So mean free path, that is the average distance between two traveled gas molecules between collisions with the wall container and other. That is known as the mean free path of a gas. Now the diagram shows how the molecule travels and what is the collision between the wall and container wall and vessel walls. The mean free path in a vacuum is very large. The molecules have a higher probability of colliding with walls of the vacuum chamber rather than with each other. So there is the higher probability colliding with wall rather than interact with each other. So when we gas molecule mean free path in air at ambient room temperature, that time mean free path, that is the lambda, is equal to 0.67 upon pressure in Pascal or 0.005 upon pressure. So you will get that mean free path of a gas molecule for air at ambient. So following table it shows the various pressure at room temperature of it. So your first row is the pressure in millibar and second one is the mean free path in cent. So when it is the pressure is the 1 into 10 raised to 3, that time you will get the 7 into 10 raised to 6. When it is the 1, you will get the 7 into 10 raised to 6. When it is the 1 into 10 raised to minus 3, you will get the 7. And when it is the 1 into 10 raised to 6, you will get the 7 into 10 raised to. When it is the 1 into 10 raised to 9, you will get the 6 to 6. So there is the some 0.00 suction relation between A and pressure of the air. And now next concept is the monolayer time. So that is the concept of one can define the time for monolayer formation, which is the time required for a freshly formed surface to become covered with monolayer of gas. When a monolayer gas molecules form at the surface, so that time, what time is it? That is, so it is the is equal to n mono upon z. So it is the impeachment rate. So it is the monolar formation time. N is the n mono is the number of n is the centimeter 10 raised to. The typical number of molecule surface is n mono. N mono is around 1 into 10 raised to 50 molecules per second. For air room temperature, the monolayer time can be expressed as tau is equal to 3.2 into 10 raised to minus 6 upon. So where P is the pressure monolayer. Next one is the collision rate. So collision rate between a gas molecules each other and the tenor of the US. So one can consider the volumetric collision rate, which is the number of collision occurring per unit volume per unit. So collision rate is denoted by Z is equal to 5.27 into 10 raised to above mean free temperature months, that is the Tm, that is term X. So here Z is the volume collision rate, that is the per centimeter cube per second. M is the molar mass, gram per. T is the pressure, that is the millibar. T is the temperature, kg. Lambda is the mean free path. So that is the collision rate. Now see the table, so which gives the or clear the what is the idea of collision rate and other rate, impeachment rate, free path and pressure and voltaire. So is related with the various vacuum level or pressure. So first column is the vacuum type. So there is the some type of vacuum. Second one is the pressure. Third one is the mean free path. Third one is the impeachment rate, collision rate, and last one is the monolayer formation. So when it is a vacuum type low, pressure is the 10 raised to 3, mean free path is the 10 raised to minus 5, impeachment rate is the 10 raised to 23, and collision is the 10 raised to 23, and monolayer formation time is a 1 nanometers. So there is the only mean free path is the minimum in a low vacuum, pressure, impeachment rate, collision, these are the. So we have to see how to, when we increase type of vacuum, so when we is pressure range, then mean free path is increase, impeachment rate is decrease, collision rate also decrease, and monolayer formation time is required. So it is in medium 10⁻⁶ means microsecond, I is the millisecond, and variation. So that is the intercorrelation between this value terms. First is the pressure, lengthy bar, diffusion rate, collision rate, monolayer formation. These higher systems are the correlated totally depend on the path or what type of level of gas is present. Now, next one is the gas transport properties. So, when you transfer or transport gas, so there is some properties and changes. So, how gas can transport momentum, energy, or particles from one place to another. It considers non-equilibrium situations, but still in the steady state. That is, so that the system parameters are time independent, but the surroundings will be time dependent. This phenomena is examined by called transports, and the following are first one is the viscosity, which is the transport of movement. Second one is the thermal conductivity, which is transport of heat. And third one is the diffusion, which is the transport of particles. So when we transport the gas, so that time we have to consider three main parameters. First one is the viscosity, which is related with transport of momentum. Second one is the thermal conductivity, which is transport of heat, and third one is the diffusion, which is transport of. So that is the concept of gas transport. So how gas? So starting with a first parameter, that is the viscosity. There are three important properties of the viscosity of a dilute gas that seems to defy common sense. The first property is the lack of dependence on pressure or density. Intuition can suggest that gas viscosity should increase with increased density, but viscosity is actually independent of density. So gas viscosity increases with increases the gas density, but gas viscosity is actually independent of the gas density. The second unusual property of viscosity is its relationship with temperature. The viscosity increases as the temperature is increased. When the temperature is increased, the viscosity of gas particles starts. The third property pertains the viscosity of pressure. That is there is no obvious correlation of gas viscosity to molecular. So heavy gases are often more viscous than light gases, but there are many exceptions and no simple pattern. So here main thing is that heavy gases are very viscous than the light gases. So that is the concept of viscosity of a dilute gas or dilute gas transport. Second one is a thermal conductivity. The property of the thermal conductivity of dilute gases parallel of those of viscosity in some respects. The most striking is the lack of dependence on pressure or density. The thermal conductivity of dilute gas increases with increased temperature, much like its viscosity. So already we have discussed the temperature increase, then viscosity of gases. So same as thermal conductivity is also depend on the temperature. When it is the temperature increase, the thermal conductivity of gas is increases. So this appears to be related to the different effect that molecular weight has on thermal conductivity and viscosity. Light gases are usually better conductors than heavy gases. So light gas is the very good conductor or better conductor than heavy gas. So you can easily conduct light gases than heavy gases. Now next concept or third property of point of a transport of gas is a diffusion. Diffusion in dilute gases is in some ways more complex or at least more than either viscosity and thermal. So diffusion is the very complex or complicated than other viscosity and thermal conduction. So which is light molecules at higher average speed than the heavy molecules at speed. And if a light or heavy gas are inter diffusion, the light molecule should move into the heavy gas region fast than the heavy molecules move into the light gas region, thereby causing the pressure to rise in the heavy gas region. The composition difference in a two-component gas mixture causes a relative flow of the components that tends to make the composition uniform. So that is the concept of diffusion of a transport properties. Now the flow of one component is proportional to its concentration difference, and in an equal counter current this is balanced by an equal and opposite flow of the other component. The constant of proportionality is the same for both components and is called as a diffusion coefficient for the gas. The diffusion coefficient are inversely proportional to total pressure or total molar density of gas and are therefore reported by convention at a standard pressure of 1 atmosphere. Diffusion coefficient increases with increasing temperature at a rate that depends on whether the pressure or the total molar density is held constant as the temperature is changed. So diffusion coefficient is the very important in the diffusion of a gas. So that depend on the pressure, total molar density at constant. Now that table shows the how do these three parameters of transport property of complex. So first one is the viscosity, that is the transported property. One is the momentum. Thermal conduction, that is the transported property. That's diffusion. So what is the kinetic relation or theory of that property? That is the absolute viscosity is equal to 1 by 3 nm. So lambda is the mean free path, m is the molecular mass in kg, velocity in meter per second, absolute viscosity, n is the gas density in per meter, that is the kg per meter. And second one is the thermal conduction, that is the k is equal to 1 by 3 lambda v cv. So cvm is the molar heat capacity at constant value, and K is the heat conductivity. So it is denoted by joule per Kelvin meter per meter second. Diffusion is denoted by D is equal to 1 by 2. There is the lambda is the mean free path in millimeter and meter. V is the velocity in meter per second. V is the coefficient. So meter square per second. So that is the units of. Now next concept is the ranges of vacuum. So we have to know the 6 types of ranges of vacuum and their pressure range and application. First one is the low vacuum range, that is the atmospheric pressure to 1 millibar. Application vacuum cleaner, mechanical handling, vacuum forming. Second one is the medium vacuum range, that is the pressure range is a 1 to 10 raised to minus 3, and applications are vacuum drying, vacuum freeze for a food industry. Third one is the high vacuum range. Their pressure range is the 10 raised to minus 3 to 10 raised to minus 6 millibar. So there is the application of production of microwave, light bulbs, paper demolition. And next one is the very high vacuum range, 10 raised to minus 6 to 10 raised to minus 9 millibar. That is the pressure range. The application are electron microscope, X-ray, gas discharge tube, electron beam. Next one is the very high vacuum range. So their pressure range is the 10 raised to minus 9 to 10 raised to minus 12. So that application of particle accelerator, space simulator, material research, and semiconductors. And last one is the extreme high vacuum range, that is denoted by XHV, for their pressure range is less than 10 raised to minus 2. The applications are particle accelerator, space simulator, advanced semiconductor classes. So these are the various vacuum ranges and their pressure ranges and shifts. Now next concept is the gas conductance of a vacuum. So the flow of gas in a pipe is dependent on the pressure drop across the object as well as its cross-section geometry. So conductance is the ratio of throughput under the steady state conversion condition to the pressure differential between two specified isobaric sections inside the pumping system. So here conductance is dependent upon throughput of a pumping system and the pressure difference between two specified isobaric sections, the Q and P. So you will get the conductance of one pumping system. So C is equal to throughput, that is the Q, upon P2 minus 1, that is the two differential pressure. The SI unit of conductance is meter per second or meter cube per second. The conductance depends on the temperature, gas species, geometry, and the pressure in the viscous. The gas throughput is directly proportional to the pressure difference, and the conductance is the constant of proportion. So throughput is equal to conductance into pressure difference, that is the P2 minus. Now next concept is the gas impedance of a vacuum line. So when the gas flow through a pipe, the pipe will exert a resistance on that flow which has the impedance of gas impedance of a vacuum, that is denoted by PHCT. When a gas flow flowing through that pipe, that time that pipe exerts a resistance that flow that time which gives impedance of gas. The impedance will cause a pressure drop along the pipe, that is the P2 minus P1, and the reciprocal impedance is the conductance. So conductance and impedance is the inversely proportional relation. So C is equal to 1 upon Z. So throughput is equal to 1 upon Z P2 minus. So total impedance of gas drop along pipe connected Z is equal to Z1, Z2 up to Z. And total impedance of gas drop along pipe connected in a parallel. 1 upon Z is equal to 1 upon Z1 plus 1 upon Z2 up to 1 upon Z. So here Z is equal to 1 upon Q, or you have to say the Z is equal to 1 upon Q, P2 minus the gas impedance. Next concept is the pumping speed. So pumping speed is defined as the ratio of the throughput, that's the Q, of given gas to the partial pressure of that gas at a specific point near the inlet port of the pump. So the pumping speed is the ratio of throughput and partial pressure of that gas at a specific point near the inlet port of the pump. When a pump is used to remove the gas from a system, the rate at which the gas is removed is the pumping speed S, that is the L per second, meter per second, which is defined as the volume gas per unit time, that is the volumetric flow rate, which is the pump removes from the system at the pressure existing at the inlet of the pump. So S is equal to B inlet is equal to Q2. The effective pumping speed is equal to 1 upon S effective is equal to 1 upon S and 1 upon C. Less formally, it is the volume of gas at any pressure that is removed from the system by the pump in unit. The pumping speed, a measure of the pump's capacity to remove gas from the so pumping speed is the measure of the pumping capacity to remove gas from the chamber. So its units liter per second or meter cube per second. Now next one concept is the throughput or gas load, that is the gives the gas flow. Throughput and gas load can be defined as the quantity of gas in pressure or volume units in a unit time past some location in the system. The units are torr into liters per second or Pascal per meter cube per second. The throughput Q or PV flow, that is the millibar 1 per second, liter per second, is the quantity of gas is expressed in pressure value. So that is the P into P. Units at specific temperature following per unit time across a specific cross section. So Q is equal to QPV is equal to P in. The relation between the throughput and pumping speed at the entrance of the pump can be expressed as Q is equal to 2, which is the throughput, is the pumping speed, and is the pressure. Knowing the temperature and throughput, we can calculate the mass of gas following past some point in once. Although throughput and gas load are sometimes used interchangeably, it is preferable to reserve throughput as a property of the pumping system and gas load as a property of the chamber. Then we can state that at a dynamic, so we have to say when it is the gas in is equal to gas, or we have to say gas load is equal to. Now gas flow physics. So the physics of gas flow depends upon the relation between the mean free path of molecular collision and characteristics dimension of the pipe. So it has the two main gas flow regimes. First one is the molecular flow regime and second one is the viscous flow regime. When at a low pressure, all collisions are more prevalent than collision with other molecules. Consequently, gaseous throughput is dependent upon the geometry of the pipe and density differential, but not upon the absolute density of the gas. This is termed the pre-molecular flow. And second one is the viscous flow regime. At high pressure, the collision with other molecules are frequent. The flow of an individual molecule is determined by the neighboring molecules and their net rather than by all collisions. This is termed as viscous flow. So that is the two main difference between a gas flow regime, that is the molecular flow regime, and viscous flow regime. So that is the number of flow of gases. First is the flow through a tubes, and second is the flow through a compartment. So we have to see the diagram how to gas flow through a tubes, how to gas flow through a compartment. So upward diagram is the gas flow through a tubes, second is the gas flow through a compartment. So there is a differentiate between a viscous and molecular flow. First, the differentiate of viscous and molecular flow is differentiated by various parameters. So starting with pressure range, viscous flow is the high and molecular flow is the low. Second parameter is the vacuum range. Viscous flow is the low vacuum. Molecular flow is the high. Next one is the mean free path of gas molecule. In viscous flow shorter, molecular flow is the long. Next parameter, collision rate between molecules. In viscous flow much higher than that of molecules and moles, and molecular flow much lower than that of molecules and moles. Next one is the Knudsen's number is equal to index of viscous upon molecular flow. That is the K is equal to lambda upon T. So here viscous flow K is less than 0.01 and molecular flow K is greater than 0. And next parameter is the types of flow. In viscous flow there is the two types of flow. First one is the laminar flow and second one is the turbulent. And in molecular flow there is the constant flow. There is the none types of. Next parameter is the gas molecule behave like as in viscous flow, continuous particle flow, and molecular it is the discrete particle. Next parameter is the gas density. In viscous flow is the dense and in molecular flow is the scattered. Next parameter is the interaction of molecules. In viscous flow is frequently, in molecular flow is, so that is the difference between a viscous and molecular flow by a various factor. Now next concept is the pump down time. So the application decides the degree of freedom. Depending upon the application, required pump down time is determined. Pump down time helps in selection of vacuum pump. Hence there is a need to study the pump down time of vacuum system. Consider a closed system as shown in the figure in next slide. Let the initial pressure in the system Pi, that is the initial pressure. After vacuuming, let the final pressure in the system, that is the PF, final pressure. The amount of time taken by a vacuum pump to reduce pressure from Pi to PF, initial pressure to final pressure, is known as pump down time. So time required for to reduce the pressure from initial pressure to final pressure is known as pump down time. Now next concept is the pump down time derivation. So see the both the diagrams. So here one container, so there is the M of molecular gas out, here is the throughput, and the vacuum pump, that is the initial pressure, Pi, and C is the conductance. So consider a closed cavity vacuum pump system as shown. Let the mass flow rate leaving the system be M out. So mathematically M out is equal to rho into S. So here rho and SS are the density of a gas molecules, and second one is the pumping speed of system. Now second diagram, let the total inflow due to a gas leak and out gas. Maybe it can also be written as Mi is equal to Qi upon R. So throughput of input upon R. So applying mass conversion to the system, we have get Mi minus Mout is equal to dm upon. So from this definition of molar density, we have Mi minus Mout is equal to M d rho upon dt. So M is equal to rho. Now rho is equal to P upon RT. By using ideal gas law, we have Mi minus Mout is equal to P upon RT into dP by. So here RT term is outside the bracket and rho term the P upon RT. So you will get the P upon T. Combining the MI and M out, following equation we have here QI upon RT PSS upon RT is equal to V upon RT dQ by. So by solving this equation, RT term are cancelled from both sides. So you will get the dP upon dt. So QI upon V. So that V terms is going to that denominator, that side denominator, and PSS upon P. So that equation is valid for any vacuum system. It is important to note that both QI and SS are time dependent function. That is, QI is equal to F1t and SS is equal to F2t. The equation can be integrated analytically or if the transient variation of QI and SS are at steady state or after a long time, the changes in pressure with time are negligibly small. So we can write mathematically dP upon dt is equal to 0. So we get Pu is equal to Qi upon SS. So P is equal to the pressure at steady state is called ultimate pressure. The pressure at steady state is called as ultimate pressure. It is the minimum possible pressure that can be achieved using a certain pump. So it is important to note that for most of the pumps, SP is constant in its operating pressure. Also, in a free molecular region, conductance C is independent of pressure, which mathematically expressed as 1 upon SS is equal to 1 upon SP plus 1 upon C, with SP and CO being constant. From the above equation, it is clear that SS is also a constant or it's independent of pressure. Therefore, a constant SS, the equation can be integrated with the following limits, which is expressed as dP upon d. So you will get the Qi upon d minus SS into P upon d. So the limits are t is equal to 0 to t, p is equal to p1 to p. So you will get the p1 to p2 v dt upon Qi minus SS is equal to 0 to t2. By solving, you will get the minus v upon SS ln Qi minus SS. The range of P1 P2 is equal to t of 0 to t. So by solving or putting that value, you will get the pump down time, that is the TP, is equal to V upon SS ln. So put the value of that P1 and P2. So P1 upon P2. So P1 minus, that is the ultimate pressure, and second one upon P2 minus. So you will get the pump down